Let's do another example of conservation of momentum. This one will be a little bit of a different style for a couple reasons. Number one, this problem that you have on your screen here is, instead of being a collision, it's an explosion, which is the opposite of a collision. Conservation of momentum still applies, but in this case, the objects start out stuck together and then fly apart from one another. But again, although we don't know anything about how an explosion works, we can say that no matter how the explosion works, because the pieces have to gain their momentum by pushing off of each other, the total momentum has to be the same before and after. So that's difference number one. Difference number two, there's 3 objects in this system instead of 2. And then third difference is that this is a 2-dimensional problem. So this is a much higher difficulty level of conservation of momentum problem. But let's do it. So we are given a picture here. So a grenade explodes into pieces. The velocity of the 3 pieces is given. 2 of the speeds are unknown. All the angles are known. And we have the masses of each piece. Step 1, identify the system. So the system consists of all 3 pieces added together. Number 2, identify the initial and final states. Now, this is a problem where this is actually a little bit tricky. I gave this problem on an exam one time, and to my surprise, a lot of people did not know whether the drawing here was the initial or the final state, and had no idea what the other state was. Remember that in a conservation of momentum problem, there always has to be 2 states, an initial and a final. So there's only 1 state given in the question here. So there must be more information buried in this very brief question. So first of all, let's read the question carefully. It says that the grenade is initially at rest. So this is not the initial state. This is the final state. And the initial state is just going to be, if I want to add a sketch of it, it's just going to be the grenade, which has a total mass of, what is that, 7.5? 3.5 plus 2.5 is 6 plus, so that's 7.5 total mass. And it's at rest. So make sure that you identify and sketch the initial state and the final state before you even get started. This is an example of a problem where if you're not thinking step by step clearly, that can really throw you for a loop. And I'm using the standard coordinate system. So this is my plus x direction, and this is my plus y direction. It's a 2-dimensional problem. Next thing I need to do is write down the momentum in the initial state and the momentum in the final state. This is a 2D problem, so I'll do x in the left column, and I'll do y in the right column, because we need to clearly separate our x and y as always. So for the initial, super easy. Since it has 0 velocity, it also has 0 momentum. So initial x momentum is 0, initial y momentum 0. Now writing down the final momentum is going to be a real pain in the neck here. It's going to have 3 terms, and 2 of them are going to have to be broken into components. So let's do it one by one. Let's start with this guy here, the 4 meter per second guy. Let's call that number 3, because 1 and 2 are already taken. So P3x, let's start there. P3x is going to be 0, because the momentum of this object here, its velocity only is in the y direction. So it has no x component. So the x component is 0. What about the y component? So we're going to have P3y. It's negative, and it's going to be mv, so 3.5 times 4. And that's going to be 14, I believe. Just double check. I don't want to make a mistake. Minus 14 kilogram meter divided by second. Okay, so that guy's done. Now let's do, how about P1? P1x. So now I'm looking at this guy. All right, so first of all, is the x component of velocity positive or negative? It's negative. We're going to have mv and then cosine 35, because if I break that velocity into components, it's cosine 35. So it's going to be I'm going to drop my units at this point because this is going to get messy. 1.5 v1 cos 35. Then p1y is positive, and that'll be 1.5 v1 sine of 35. And then finally, P2 is this guy. So P2x, we've got positive because it's to the right. 2.5 is the mass, V2 is the velocity, and then cosine 55 to get the right component. Then over here, we'll have P2y. So that's positive because it's up. 2.5 V2 sine of 55. Okay. And the total final momentum is going to be the sum of these three, P1, P2, P3. So I'm not going to try to write that in one line right now because that's going to be kind of a bear to write down. So let's just do the whole thing at once here. Next thing we need to do is set initial momentum x equals final momentum x. That's my conservation of momentum equation. So initial momentum 0, final momentum, we've got 0 minus 1.5 v1 cos 35 plus 2.5 v2 cos 55. So there's my x conservation of momentum equation. And over to here, my y conservation of momentum equation is going to be 0 equals minus 14 plus 1.5 v1 sine of 35 plus 2.5 v2 sine of 55. So in principle, I'm pretty much done at this point. I have a system of two equations with two unknowns. My two unknowns are v1 and v2, which is what I'm trying to solve for. And I have two equations, so I should be in good shape. The rest is just algebra, which I'll go through, but the rest of this video is just going to be some tedious solving of systems of equations, if you want to skip it. Well, let's do it for the people who want to see it. The first thing I would want to do is start with the x equation and write down, because that one's simpler. My general advice with systems of equation is start with the simpler one and work your way up. So I want to solve this equation for one of the two variables. I'm kind of out of space here, so let me skip some steps. Let's solve for v1, let's say. So if I solved for v1, I would end up getting, so I would have v2 times 2.5 times cosine of 55 divided by 1.5 divided by cosine of 35, and we'll get v1 is 1.17 times v2. So that's the final punchline of that equation. Then bring the result of that equation over to the y direction. And let's move the 14 to the other side of the equation to save a little bit of space. So we'll get 14 equals 1.5 sine of 35 times, now substitute in your result from the other equation, 1.17 v2, and then plus 2.5 v2 sine of 55. Then crunch these numbers, 1.5 times sine of 35 times 1.17 is 1.01 v2 plus 2.5 times sine of 55 is 2.05 V2, which means we have 14 equals 3.06 V2. So 14 over 3.06. I got V2 equals 4.58 meters per second. Hopefully that's correct. I may have made a mistake in the algebra here. I'll just warn you because this one's a little bit annoying. Then we go over to the X column again, and V1 is going to be 1.17 times 4.58. So take my result times 1.17, and I got 5.35 meters per second. Okay. And again, take those final results with a small grain of salt because it's possible I could have made an algebra mistake in solving that system because I was skipping a lot of steps. But that's the basic idea of how you would solve this. The most important thing to keep in mind in this problem is this is a difficult, intimidating problem, but it's not that hard if you follow the steps. You know, draw the initial state, draw the final state, write down the momentum in the initial state, write down the momentum in the final state, set them equal to each other, solve the system. That's all there was to it.